3-1, solving systems using tables and graphs. So in this section, our objective is to solve a linear system using a graph or a table. Okay? What we should know by the end is that to solve a system of equations, we're going to find a set of values, then replace the variables in the equations to make the equations true. That's what we're trying to do. Okay? This is probably the most inefficient way to solve a system of equations, and we'll see why it could work or it couldn't work. Okay, so let's first figure out what we're trying to do with a linear system like that. Let's look at this little word problem right here. Okay? There's 25 bikes and trikes at the park. Okay? The bikes and trikes have 60 wheels in all. In the graph, the red dots show the sums of 25. The blue dots show 60 wheel combinations. How many bikes and trikes are there in a park? Okay, so we could figure this out based on the graph. If we looked at this red line right here, we can see that if we have 25 sums of 25, how many bikes could there be, how many tricycles can there be, whatever. Okay, so we could have 0 bikes and 24 trikes. We could have 1 bike, or sorry, 25. We could have 1 bike and 24 trikes, and we can sort of, you know, graph this line all the way down somewhere. Okay, then if we look at the blue line, we can show 60 wheel combinations, right? We could have 0 bikes and 20 trikes, and we can graph this. And at some point, if we kept these going, the red line and the blue line would eventually cross each other. And what that would tell us was that would tell us where the 60 wheel combinations and the 25 wheel combinations, right, where all of those, where it has the same number of bicycles and the same number of tricycles. Okay? So what we're going to try to do here is we're going to try to solve the linear system by graphing a line. Okay? And we'll see how to do that. Okay? So when you have 2 or more related unknowns, you may be able to represent the relationship with a system of equations, a set of 2 or more equations. Okay? That's what a system is. So my system of equations is going to be 2 or more. Or more because if we, and we'll see this in a later section, but if we have 2 variables, in order to solve that system, we need 2 equations. If we have 3 variables, in order to solve that system, we need 3 equations. And so on and so on. For 4 variables, we would need 4 equations. Okay? So what we're going to focus on in this section, in the next few sections anyway, are linear systems. Okay, these are going to be stuff with linear equations. And my solution is going to be a set of values for the variables that makes all the equations true. That's important. Not just one, right? My solution has to make sure that it's going to satisfy every equation in there, all equations. Okay? And we can solve this, in this section anyway, using a graph or using a table. And then we'll see how to solve it algebraically in the next section. So first, if I want to solve this with a graph, the best way to graph these 2 lines is using slope-intercept form. So let me write my first equation, negative 3x plus 2y is equal to 8. Okay. And let me change this to slope-intercept form. So I'm going to add 3x to both sides. And so I'm left with 2y is equal to 3x plus 8. And I'm going to divide by 2. Remember, I have to divide everything by 2. So that's going to be y is going to be equal to 3 over 2x plus 4. And now let me graph this one. Let's graph it in red. So that's going to be, my intercept point is going to be 4. So I put a dot at 4. My slope is 3 over 2. So that means up 3 over 2. Okay? And, or I can go down 3, left 2. Either way. So let's make a nice, hopefully mostly straight line. Okay? My next equation is x plus 2y is equal to negative 8. I'm going to put this into slope-intercept form, and I'm going to subtract x from both sides. 2y is going to be equal to negative x minus 8. Divide by 2. So y is going to be equal to negative 1/2 x minus 4. Okay. Let's graph this one in blue. So my intercept point is now going to be -4. So I put a dot right there. And now my slope is down 1, right 2, or up 1, left 2. Okay? And I have my line. Now my solution is going to be the point where these two lines intersect, which is right about there. And so my point of intersection is going to be -4 and -2. If I want to be sure that that is correct, I can plug -4 in for x and -2 in for y and make sure that in the first equation it equals 8, in the second equation it equals -8. Remember, for this to be the solution, it has to solve both equations because the black point is on both the red line and the blue line, so it should work for both equations. Now, a problem can happen here when we are graphing if we don't graph very carefully. Okay? So if I'm graphing my blue line over again, and I say my intercept is -4, my slope is down 1/2, there's my 2 points, but I kind of try to draw my line too fast, and, and I get something that looks kind of like that. And then maybe I draw my red line again, and I drew it kind of badly, and so now look at my point of intersection is over here. Okay? Obviously, those lines aren't very straight. They're not very well drawn. So when you are trying to solve a system with graphing, you have to be very careful about drawing your lines, especially very straight, and being sure they go through all the right points, which is why they're slightly inaccurate. Okay? Let's try another one. Okay? Let's try this one. Luckily, this graph is already set up in slope-intercept form. So my first equation is going to be +3. So I'm going to put a 3 there. My slope is up 5/2 and right 2. So here's my line. Oh, very, very poorly drawn. Okay, let's try that again. Okay, and then my next line is going to start at -1, and my slope is going to be up 1/2. Okay, and my line then is going to go like this. Okay. And I see that I have a point of intersection right about there, okay, which is at -2, -2. So that's D. Okay. Let's take a look at using a table. Okay. So in this problem, the diagrams on the right show the birth lengths and growth rates of 2 species of shark. If the growth rate stays the same, at what age would a spiny dogfish and a Greenland shark be the same length? So let's set up an equation first for this one. We have that information right there, that the growth rate is 75 centimeters a year and the length is 37. So let's set up an equation that says y is going to be equal to 0.75 times x plus 37. And then let's use this information right there for the dogfish shark that says that y is going to be equal to 1.5x plus 22. Okay, so now I have some information. What I'm looking for when I set up a table, okay, I'm going to set my x values. Let's call that y1 and y2. So we're going to have y1 and we're going to have y2. So my input, whatever I choose for my input, I'm going to have to get 2 outputs. So what I'm looking for is I want to find the point, the input, that these 2 outputs are going to be equal to the same thing. So let's try it. If I plug in 0, right, I would get 37 for y1, 22 for y2. Okay, so if I start to plug in other numbers, like let's plug in 10. Okay? Plugging in 10 gives me 37 plus, okay, that gives me 44.5 for my Greenland shark and 37 for my dogfish shark. So now looking at this data, right, the Greenland shark data is still, the Greenland shark is still bigger than the dogfish shark. So I still haven't got to the point where they're going to be the same. So I haven't gone too far. So let's try another number. Let's try 20. Plugging in 20, multiply it by 0.75, add 37, I get 52. Plugging it into the dogfish equation gives me 52. And that's what I'm looking for. I'm looking for the place where these two sharks are the same length, and that is the solution to the system. So my input would be 20, my output would be 52. Okay? And if I were to graph these things, which I didn't probably really want to do because my system was a little bit more difficult to graph, had some bigger numbers in it. Okay? My system now is, I have the point where these two lines intersect if I had graphed them, but I can do that solving with a table if I want to. Okay. Next, let's talk about the different types of classifications a system of two linear equations can have. And we can tell by the number of solutions that the system has. Okay? A consistent system has one solution, at least one solution. And there's two types of consistent systems: consistent independent, consistent dependent. A consistent independent solution has, a consistent independent system has one solution. A consistent dependent system has infinite solutions. And then finally, an inconsistent system has no solution. So we have three types. We have independent, dependent, and inconsistent. Independent, one solution. Dependent, infinite solution. And inconsistent is no solutions. Okay? If we look at the graphs of these things, the graph of an inconsistent system is two lines that never intersect. That has to be parallel. Okay? That's why there's no solutions. For a dependent system, for something that has an infinite number of solutions, if we have two lines that intersect everywhere, okay, these two lines have to be exactly the same on top of each other. Okay? So they're going to represent the same line. And here's a picture. Okay? So when we have two intersecting lines that intersect at one point, okay, that's going to be consistent independent. These two lines, right? The purple one has two lines on top of each other, a red and a blue. That's a consistent dependent system. And then the parallel lines over on the right, that is no solution. They are inconsistent. Here, my slopes have to be different. Okay? And then the intercepts don't matter. For coinciding lines, for a dependent system, same slope and same intercept point, same y-intercept point. Okay? If two lines have the same slope and the same y-intercept, okay, they have to be the same line. And for parallel, right, we have the same slope and different y-intercept. Okay? So based on the slopes and the intercepts, we can tell what kind of system that we have. And that's what this question says. Is the system, without graphing, is this system independent, dependent, or inconsistent? Well, the best way to tell is to put it into slope-intercept form. So here's my first equation. 4y minus 2x is equal to 6. Right? Changing this into slope-intercept form, subtracting 4y from both sides gives me negative 2x equals negative 4y plus 6. Divide by negative, oops, here we go. Made a little mistake there. Going it the wrong way. So 4y minus 2x is equal to 6. Have to isolate y, not x. So we have 4y is equal to 2x plus 6. Right? We want to move the x over to the other side. We want to add 2x to both sides. Divide by 4 gives me y is going to be equal to 1/2 x plus 6 over 4. That's going to simplify to 3 over 2. Okay, so there's my equation. There's my first equation in slope-intercept form. Let's do the second one. So my second one is 8y is equal to 4x minus 12. We're going to divide everything by 8. So that gives me y is going to be equal to 1 half x again. That's good. Minus 3 over 2. So now, if we notice, my slopes are the same. But my y-intercepts are different. Same number, but different sign. That means they're different. So when slopes are the same and the intercepts are different, that is an inconsistent system, right? Those two lines are parallel. Okay. If I were to change that to a plus, now there would be dependent system, because now the two intercepts are exactly the same. And finally, if I change one of the slopes, now I have an independent system. Even though the intercepts are the same, the slopes are different, which means that my two lines are going to intersect at one spot. Okay. Which one of these is inconsistent? Well, how can you tell? You want to isolate, put into slope-intercept form, and see which one gives you something that has the same slope but different intercept points. Okay? C is going to be the answer, and it is because we can divide this equation by 2. That gives me y is going to be equal to negative 2x plus 2. And then when I solve the first one for y, when I set it into slope-intercept form, 6x plus 3y is equal to 12. Subtract 6x from both sides. I got 3y is equal to negative 6x plus 12. Divide everything by 3. So y is going to be equal to negative 2x plus 4. Same slope, different intercept. That's inconsistent. Same slope, same intercept. That's dependent. Same slope, or sorry, different slope. That's independent. Okay. Which ordered pair of numbers is the solution to the system? So in order to figure that out, all you would have to do is plug in the numbers and figure out which one actually works for the system.